do have to start with the VM diagram because we know, at least for a homogeneous uniform beam along its length, that the place, at least along the length that we're going to see the highest stress is where we have the highest shear force. So that'll tell us where in the, I'll call it the x direction it is. Then to go in the stress, we're going to have to see where along the z direction is that stress going to be maximized. So the first step, right, where is V the maximum? Because if we maximize V, we're then going to also be maximizing tau in the VQ over IB calculation. So where we want to start here is starting with our VM diagram. Since we don't know up front where along the length V is going to be the maximum. Right, so if I sum forces in the x direction, y direction, once I designate them, I won't go through these steps, but you're going to get that at the pin at A, 1.5 kip, and the roller at B, 7.5 kip. We want to then use that to make our VM diagram so we can identify what the value of V is everywhere along the beam, and then ultimately what the maximum value is going to be. And for this example, I only care about the shear stress. In general, though, I probably want to know what the maximum shear stress is and what the maximum normal stress is, bending stress is. So for this one, I really only need the V part of the diagram. I won't make the M part for this, but in general, I probably would. I have all my critical lines drawn where I have a point load at 6. I have the point load from B of 7.5 kip. And here I only have point loads. I don't have any distributed loads. So I just need to follow the direction of my point loads. So at the extreme left, I'm going to go up by 1.5. Between these lines, nothing happens, so I'm going to remain stationary at 1.5. 1 foot in, I have a point load of 6 kip, so I'm going to drop down from 1.5 by 6. And I'm going to go down to negative 4.5 kip. Between the lines, nothing's happening, so I stay at negative 4.5 kip. 2 feet in, I'm going to go up by 7.5. So negative 4.5 plus the 7.5 brings me up to 3. There's no distributed load here, so I stay at 3 kip. And then at the end, I have a point load of 3 kip, which will bring me back down to 0. So I start at 0, end at 0, so this presumably is the correct V diagram. In the interest of time on this one, I won't make the M diagram, but we might be interested in that as well if we want to find the maximum normal stress due to bending in the beam also. So in this one, for the V, what we want to identify is really the absolute maximum value. Because as I said, for most materials we're going to deal with, they're going to behave the same whether the shear force is up or the shear force is down, or the shear stress is up, shear stress is down. So the sign we don't really care about for V. For M we do, because compression and tension, things potentially are going to behave differently. But for the shear stress, we don't really care. So what we can see here is that the absolute maximum value is going to be 4.5 kip. And really it's along this entire section, the beam is experiencing 4.5 kips of internal shear force. So the maximum V, ignoring the sign for right now, 4.5 kip. So we have one piece done for this beam. We know where along the beam we need to analyze for the maximum shear stress. And it's going to be the same anywhere from 2 feet to 3 feet, because that's where the shear force is maximum, 4.5 kip. But to get the shear stress, the V is taken care of. I'll still need to know Q, I, and B to do the rest of this problem. I'm looking for the maximum shear stress. So where should I look? I know now in the x direction where to look, but now where in the y direction do I want to look between 2 feet and 3 feet? So where in the y direction along the cross section do I want to look to find where the shear stress will be maximized? Right, specifically the neutral axis is usually where my shear stress is going to be maximum. So the location in the y direction dictates what I'll use for Q and what I'll use for B. But actually, I will be independent of that. So let's take a step back. We can find I without knowing where along the cross-section we want to find the stress, because the cross-section doesn't change in that from 2 feet to 3 feet. So let's find the value of I. Fortunately, this is a pretty straightforward cross-section here because it's rectangular. 6 inches by 3 inches. We don't have to use the whole tabular method for this one because it's just one rectangle. So we can compute it directly. It's just going to be its height of 6 times 6 cubed times 3 over 12 is going to be 54 inches to the 4th power. Again, the value of I, it doesn't matter where along the height we want to be measuring the stress, I will be the same at any location. It's Q that will change and B that would change. Oh, and for this we know that the neutral axis is going to be at half of its height, so 3 inches above the bottom. I we've taken care of, V we've taken care of. Now, depending on where we are along what I'm calling the y direction, is going to change the value of Q and the value of B. And now this is where we have to be concerned of what are we actually looking for. In this case, we want the maximum shear stress. And like you just said, most of the time the maximum shear stress happens at the neutral axis. So this, we're going to make another picture to determine our value of Q and our value of B based on where we want to find that shear stress. So we need another picture now. If we're cutting it at the neutral axis, this is the picture we're going to use for Q. So I'm cutting it at the neutral axis. I can take everything above that or below that. It doesn't really matter. I'll just take everything above it for this example. And now the neutral axis does pass along the bottom of that cut. And I know that the amount of material I had to cut through to make this picture was 3 inches. Which means that the value of B is 3 inches. I'll come back to that as for like a counterexample in a second here. And then the shape that I have left is going to be 3 inches by, this is now only 3 inches high. So what I need to calculate Q is of the shape I kept, I need to find what I call A prime and Y bar. Y bar, again, is going to be the distance between the centroid of this mini shape and the neutral axis from the original figure I had up here. And A prime is going to be the area of the mini shape that I made over here. So for this simple shape, what is going to be the A prime value for my mini shape that I'm using to find the value of Q? Right, so it'll be 3 inches by 3 inches, so the mini shape has an area of 9. And what's the value of Y bar for my mini shape?
1.5.
Right, 1.5, the distance between the centroid of the mini shape and my neutral axis. So at this plane, which is the one that passes through the neutral axis in this case, my value of Q is going to be 13.5 cubic inches. So I have the V from the VM diagram, I have the I from the entire cross-sectional area, and I have B and Q from knowing that I want to cut it, or I want to analyze it at the neutral axis if my interest is finding the maximum shear stress. So I can put this all together now. I'll have 4,500 pounds times 13.5 inches cubed over 54 inches to the fourth times 3 inches. And checking out our units so that we're consistent, I have inches to the third on top, I have inches to the fifth on the bottom. So my answer will be in inches squared on the bottom. I have pounds on the top and none on the bottom. So my answer will be in pounds per square inch, or more simply, PSI. And if I take all my numbers, I'm going to get that my shear stress is 375 PSI at the neutral axis. So that is the maximum anywhere along the length and along the height of my shear stress.